Hello, everyone. This lesson is going to be on energy and power, specifically electrical energy and power, although the first picture that I'm showing you here obviously has really nothing to do with electricity, but it has a great amount to do with energy and with power. So this is a scene from the Tour de France, and this is one of the mountain climbs, the Col de Tourmalet, and we can see at the lower left-hand side all of the switchbacks as the riders climb up and eventually reach the Col or the mountain pass. So all of the riders will eventually reach the top. They all expand in the end the same amount of energy, they perform the same amount of work, but their power output is not going to be the same. Energy, as we'll see, it's measured in units of joules. Work, the units are also joules. So they use the same amount of joules, but they don't use it at the same rate. And that's where power kind of ties in here. So power has to do with time and how quickly something is done. So the quicker it is done, even though the same amount of work may have been performed and energy expended, there is more power performed if it's in a shorter period of time. So power is really the rate at which work is done. So we're going to be taking a look at a number of different equations. These equations are directly from your data booklet. And I'm just going to escape out of here for a minute and pull up a couple of pages in your data booklet that I am going to be referring to. So this first one here is right away at the beginning, just a reminder of things that you don't need to remember. So all of these different prefixes. Quite often when we're talking about energy, we're talking about huge, huge, huge numbers of joules. And so we use numbers like capital M mega, capital G giga, and even the capital T for tera. So these are all really, really big numbers. So mega means whatever number times a million. Giga, whatever number times a billion, or respectively 10 to the 6 and 10 to the 9. So keep that in mind because we are going to be coming across some fairly big numbers with our calculations. And the equations for electricity, right here in your data booklet on page 3, I'm going to be talking about a few of them in here so we can see wherever we have P. It tells us on the right-hand side that is for power, and the units for power, they are in watts. But a number of different equations that we do have here, P equals IV, P equals I squared R, E equals PT. These are all different equations that we can use that do involve power calculations. So power, again, is the amount of work that is done over time. So remember that this backslash here, it does mean divide, just in case people don't remember that. So work divided by time, that is power. The units for work are joules. The units that we use for time in general are seconds for most calculations in physics. So the units for power would then be joules per second. And 1 joule per second is also equal to 1 watt. Power units can be either represented as joules per second or simply as watts, the amount of power that is performed. So work is, of course, also a form of energy, which means that if the units for work are joules, the units for energy are joules as well. They do have the same. So power, up here, we have that it's equal to work divided by time. Then we can also say that power is also energy divided by time. And all of this is really just going to deriving the equation and understanding the equation that's in your data booklet. So rewriting that, power is equal to energy divided by time. And if we just rearrange this, isolate the energy, this is the one here that is in your data booklet that you do need to know how to use and how to rearrange. So energy is equal to power times time, or we can rearrange that to solve for power, or we could rearrange it to even solve for time, and time would then be equal to energy divided by the power. So these are all different manipulations for this one formula that we have here. So I'm going to use an example of doing some power calculations and energy calculations using, well, this picture that we're taking a look at here, a holiday light supply or Christmas light display, maybe a little bit over the top in this case, but certainly a lot of lights, a lot of energy that is being consumed in order to light up this wonderful display that we see on this house. So let's do some calculations and take a look at two different kinds of lights. So these are the traditional kind of light bulbs that I grew up with for Christmas lights. So these ones here are what are called incandescent light bulbs. And these ones here in particular are C9. So these are fairly large, these light bulbs here. They're, I don't know the exact size, but probably somewhere between, oh, just a ballpark 5 to 10 centimeters in their height. These ones on the right-hand side, they're the same size. They are C9. But these are now LEDs or light emitting diodes. And those are the two that I am going to compare here. So one of the things about these ones is if the light is on and it's been on for a while, and if you stick your hand on this to unscrew that light bulb, what you will find is that it is incredibly hot. A huge amount of the energy that goes into turning on and lighting up these light bulbs is lost in the form of heat, a huge percentage. And that's a big difference between the old school incandescent and the newer LED lights, is these ones here are much, much cooler. So they are much more efficient because less energy is lost in the form of heat. Taking a look at LED compared to the old school incandescent. And that's going to lead to some of the calculations that we see and the energy efficiency of the LEDs compared to the incandescent light bulb. In fact, if you do take a look at the elements that we see inside of these incandescent lights, what we really have is something really, really, really hot that also just happens to be giving off light. So think about your toaster. If you pop some toast in your toaster, turn the lights out, what you do see is this glowing red color, but that's not really the point of the toaster. The point of the toaster is to, well, heat up your toast. And essentially, that's what we have in these light bulbs. It's releasing a huge, huge amount of heat. And as a byproduct, well, we also happen to get a little bit of light as well. But most of the energy is released in the form of heat. Anyway, for this example here, we're going to try and compare the two by saying that we want to string along 350 feet of this lighting on the outside of our house. So I just did a little bit of internet searching here, and what I found is that you can get a strand of the incandescent lights 24 feet long. And for each one of these 24 feet strands, it requires this much power in order to operate those lights. There's a 12-inch spacing, so that means, well, we actually get about 24 lights along the length of these 24 feet, and that requires 125 watts of energy. So to get 350 feet, we need to have 15 strands. For the equivalent LEDs, so equivalent, I mean they generate the same amount of light. In fact, the LEDs might even generate a little bit more light. So for these ones here, what I found is we can get some strands that are a little bit over 34 feet. The spacing is about 8 inches apart. So in fact, we would get twice as many lights when we're using the LEDs. We would need 10 strands to get our 350 feet. And for the 34 feet, this only requires 7.5 watts to run those light bulbs. And again, it's 125 to run the 12 lights, or sorry, 24 lights that we have on the 24 feet of the incandescent. Okay, so let's go ahead and do a few calculations here. So let's say that you want to be operating these holiday lights, and this is a fairly conservative number, 4 hours a day, and we'll say for 15 days in total. So some simple math here will tell us that that is now going to be 60 hours in total that we're going to be running those lights for. So how much energy does this actually require? Again, energy, the units that we use are going to be joules. Again, most of the calculations that we do in physics, we do convert into seconds. So we're just going to take our hours that we have and we're going to convert it into seconds. So here I have the 4 hours of 3,600. Where does that come from? Well, 60 minutes in an hour times 60 seconds in a minute. 60 times 60 is the 3,600 seconds per hour. So multiplying 4 times the 3,600 times the 15 days, that's how I came up with this number here of 216,000 seconds. So this is the equivalent of the 60 hours or 4 hours per day for 15 days in total. So for our first incandescent light bulb, so again, we have 125 watts per strand, but we need 15 strands. So I just multiply those together. So the total wattage for the incandescent light bulb is 1,875 watts. And this, by the way, would require you plugging it into multiple different outlets. Otherwise, you would be tripping the breakers in your house. So you would need multiple outlets for this. If we take a look at the equivalent C9 LEDs, 75 watts per strand. Now we only need 10. So I'm just going to multiply the 7.5 by 10, and we see we need a total of 75 watts for the length of 350 feet. In this case as well, whereas we need multiple outlets to plug in these incandescent lights, we could probably run all of this off of one single outlet or one single receptacle. So over the 15 days, how much power is going to be required? So what we're going to do is we're going to take this equation here. Again, this is the one that's in your data booklet. Equals PT, how much energy is required. So we're going to take the power, that's the watts, and we're going to multiply that by the time in seconds that we just calculated. Okay, so again, this is the number of watts for the 15 strands of the incandescent light bulbs, each strand requiring 125 watts. Multiply those together, we get a very big number in joules. Again, I mentioned we're talking about big numbers. So 4 times 10 to the 8 more or less, and this is 400 million joules that we are talking about here. So again, big number. Do the same calculations, exactly the same calculations with the LEDs. So same amount of time, obviously, different wattage when we're talking about the LEDs. It's still a big number, so 10 to the 7. So this is about 10 million joules. So how big of a difference is this that we're talking about? Do we really care? Well, this is what most people do care about, is what is it actually going to cost me to string up those lights and to run them for a certain period of time? Well, consumers, when they are billed by the utility companies, they are billed on what are called kilowatt hours. So how much kilowatts per hour are you consuming? And that is what they are charging you on. So kilo is 1,000 times. So whatever you have for watts, if you have that many kilowatts, you multiply it by 1,000. And hours, of course, well, we just did the conversion from hours to seconds, and now we're just going to kind of reverse that around because people are billed on the hourly rather than the second rate. So power is now, yeah, in kilowatts. So you're going to take whatever number you have, and we need to divide it by 1,000 to turn it into kilowatts, and we'll see that. The time, we're just going to go back to seconds, so we're going to divide that by the 3,600 seconds as well. So the current rate in Alberta, when I'm doing this presentation, in terms of kilowatt hours, is $0.167 per kilowatt hour of energy consumed, or that is 16.7 cents per kilowatt hour. So how we actually calculate the cost then is we take the units of energy that we are consuming, and we're going to multiply that by the cost per energy unit, which is this one right here. So let's do that for each of our different light bulbs. So for the incandescent, how many kilowatt hours do we have? So we want to take the number that we have in watts, and convert it into kilowatts. So all we're going to do is take the decimal that's right here and move it over 1, 2, 3 places, or divide it by 1,000, and that converts it into kilowatts. This is just reversing the previous calculation. It's 60 hours that we have. Multiply these two together, and this is the amount of energy, kilowatt hours, that is consumed. Exactly the same calculation for the LEDs, and hopefully you notice that, wow, this is a considerably lower number that we do see. But again, what is it actually going to cost? So let's bring that home by taking this number here, multiplying it by the cost per kilowatt hour. And that gives us almost $19 to run the lights for the period of 60 hours. And again, you might think that's not a big number, but then again, running it over the holidays for 60 hours, most people would have their lights on for much, much longer than that. The point is, though, let's take a look and compare it to the LEDs. So we have here the cost per the number of kilowatt hours times the cost per kilowatt hour. It works out to 0.75 or 75 cents to run these lights for the entire duration of 60 hours. So is there a difference? There's a 25 times less difference using the LED lights. So much, 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 much more energy efficient. And simply, it really does have to do with heat. A huge amount of the energy is released in the form of heat from the incandescent light bulbs. They're very inefficient in terms of actually generating light, and the LEDs much, much more efficient in terms of that. So I just want to talk about a couple of other equations also in your data booklet, and let me just go out of the presentation here and back into the data booklet. Take a look at that for a minute. So this is the equation that we were just using here. Energy, power, and time. We were taking a look at that. And now I want to take a look at these two up here, and I guess also this one here, which is Ohm's law. So those three there, how those equations are kind of important, and how you can also use those for power calculations, and what kind of power calculations you would use those for. So for starters here, what I do have is that we know that voltage is measured in units of volts, but we can also say that volts are the same as joules per coulomb. Current is measured in units of amps, but amps are coulombs per second. So if we take these two and multiply them together, joules per coulomb, coulombs per second, that's what we have here. The coulombs cancel out, and we end up with joules per second. So what did I just multiply together? Well, that was the volts times the current. So this here, notice that those are also the same units for power. Joules per second are the units for power. So then what we can say is that power is also equal to, well, what I have right here, which is in your data booklet that I just showed you. Power is also equal to voltage times the current. Ohm's law, of course, we can take this equation, we can rearrange it to solve not only for voltage, we can solve for current, we can solve for resistance. So just to quickly do that, if we needed to solve for current, then it would be resistance divided by voltage. If we needed to solve for resistance, it would be voltage divided by the current. So if we take this equation here, I'm just looking at that because I showed you this one here wrong. That's why I'm processing this a little bit. So our current should actually be the voltage divided by the resistance. That would be the correct one there. We're rearranging it to solve for the current. Okay, so the current, the resistance, the voltage, those are the three different rearrangements for Ohm's law. So what we can also do is we can take this equation here and we can say, okay, voltage then is also equal to IR. So now, where I have voltage, I'm just going to get rid of that, and I'm going to plug in the IR. And that's what I have down here. So IR in for the voltage, and that gives us power is equal to I squared R. So where this equation is really kind of important is when a power company, a utility company, is talking about power loss. So they want to minimize the amount of power that is lost when they're transmitting electrical energy. Any power loss means a loss in money, and power companies are not interested in losing a lot of money. So how does a power company want to minimize their power loss? Well, what they want to do is they want to keep the current that they're transmitting the electricity through the power line. They want to keep it really low, and they also want to keep the resistance really low. So those high energy power lines going from an electrical generating station to a city and to people's homes, they want to minimize the power loss, so keep the current as low as they can, keep the resistance as low as they can. And this is why utility companies, they transmit electrical energy using high voltage power lines. So those high voltage power lines, we're talking really high voltage power lines. So we might be talking 100,000 volts, or we might be talking 500,000 volts. So they're trying to transmit that energy as high as safely possible at as high of a voltage as they possibly can. And the whole idea behind doing this is they want to minimize the current, because the lower the current, the lower the power loss, and the less energy is lost in the form of heat. So this equation here, one of the previous ones rearranged, so they want to keep the current really, really low. How do we do that? Well, if we have a high voltage, voltage is in the denominator. So now if we take power and divide it by something that's really, really big, that gives us a number that's really, really small. In other words, it keeps the current low. So this is the key as to why the utility companies want to use really high voltage. Using a high voltage keeps the current low, and that means less energy is lost in the form of heat, and that means that less money is being lost as well. Much more efficient to transmit electrical energy at lower voltage, or sorry, at higher voltage and lower current. This wheel that I found here on the internet, kind of nice because it shows all these different variables, and it shows that there are many different equations that you can actually use to calculate power, many different equations for voltage, resistance, and for current as well. So I'm just going to go back again to the data booklet just to point out that, yeah, for power, we have three different equations here. So then the question is, well, which one do I use to solve the problem? And the answer is, it depends upon what information is given to you in the question. So I'm just going to go through one calculation with you here to show you what I mean by that, and show you hopefully how easy it really is to solve these problems. So this is our sample calculation. Again, read really, really carefully. So what are we asked to do? Calculate the power. That's what we're trying to find out. Calculate the power output. It's a hydroelectric generating station, and it produces a maximum current. Whenever you see numbers, that's obviously going to be important. This is a number. It's important. What is that number? Well, it tells us that it's the current. These are the units for current. This is the symbol for current. Okay, so it tells us that number. We have another number here as well. What is this number? Oh, well, V is for volts. The K, what is that? That's the kilovolts. So this is going to be whatever this number is times 1,000. Times 1,000. Okay, so we have current, we have voltage, So what equation do you use? Well, it all comes from graphs. So what we're just told is that our given information is this. Our given information is this. This tells us what's required. That's what we're trying to find out. Now it's just a matter of going to your data booklet and picking which one of those three equations is going to work. Which equation has current, has voltage, and has power. So if the equation has resistance, we don't have the resistance, so we can't use that equation. So the information that you have is going to dictate which equation you can use. So if we take a look at this one here, power is what we're trying to find out. Current we have, voltage we have, that's our equation. This one here, we don't even have to rearrange. So you could have been given the power and the voltage, and you had to solve for the current. So again, as with all equations, you need to know how to rearrange this one. So this is the version that's given to you in your data booklet, but the question might ask for current. So you need to rearrange this. The current equals power divided by the voltage. Or it might ask you for the voltage. And then you need to range it. So voltage is equal to power divided by the current. Okay, and of course, you should be able to do this, to rearrange it, to solve for whatever they are asking for in the question. So pretty straightforward with this one. We don't need to do any rearranging. All we need to do is plug our numbers in. However, this one is in kilovolts. And remember, we do need to multiply by 1,000. And that's why we have this number here. 2.5 times 10 to the 5 is 250 times the 1,000. Plug those numbers in, and again, we get a pretty darn big number that we are talking about here for the power. This G is for giga, and that is 10 to the 9. So in your calculator, it may come up as 2 or 2.0 times 10 to the 9 joules. That is exactly the same as what we see here, which is the 2 gigajoules.